So we've previously introduced the idea of a moment of inertia or rotational inertia, and I mentioned that I would show you how to actually calculate those for different shapes of objects, and I know you've been waiting for this, so the moment has finally come. Previously I told you that the moment of inertia of a single particle is equal to mr squared. And then if we have an extended object made up of presumably a bunch of particles, then we need to sum the moments of inertia of each of those particles. And if we assume a continuous distribution of mass, then we need to take each little chunk of mass times its location squared, or its distance from the axis of rotation. And then we need to add all those up, and since we have infinitesimally small pieces of mass, we need an integral. Everybody loves integrals, right? Okay, so let me show you how we can use this to do some wonderful problem solving. So if we have a cylinder that is hollow in the middle, so there's like a hole cut out of it, and the moment of inertia works out to be 1/2 times the total mass of the cylinder times the inner radius squared plus the outer radius, designated as R2 and R1. And I will show you how we can derive that from our new favorite formula of the integral of r squared dm. So we're going to start out, we need to relate the chunk of mass to its location. So in general, density is mass over volume. So if we rearrange that, each little infinitesimal chunk, each little dm, is going to be density times volume. So density, and we're going to have an infinitesimal little volume, dv, that goes with our dm. That's a terrible d, but you get the idea. So now we just need to have an expression for dv, and we'll be in business. So what we're going to do is we're going to divide this up into a bunch of rings that have a height h and a width dr. So we still have density, and then the volume of each of those rings is going to be 2 pi r, so the circle times the height of the circle, and then times the width of the circle, which is going to be dr. Okay, so that nice thing. Now we've got a relationship between dm and dr, so if we substitute this in for dm over here, to our moment of inertia equation, we get r squared times 2 pi, oh, I forgot the density, times r times h times dr. And this can clean up pretty nicely. We can pull out all the constants, so we're going to have a 2 pi times h times the density. I keep switching the orders just to keep you on your toes. We can combine these r's here to get an r cubed dr. And we want to integrate from the inner radius of r1 to the outer radius of r2, and we have a pretty simple integral to do here. So we got 2 pi h rho times r to the 4th over 4, evaluated from r1 to r2, jumping back over here. That is going to give us 2 pi h rho, might as well put the 4 out over here, and then we're going to have r2 squared, and then we're going to subtract the whole thing with r1, so we might as well just factor out that stuff out front, and we'll end up with this expression here, which isn't exactly what we're looking for. It would be a lot easier to find the moment of inertia of a cylinder just by knowing its total mass than by knowing its height and density and all of these things. So what we're going to do is we're going to substitute in for density there. So density is mass over volume. I'm going to jump over here because then I'm going to come back over there to plug it in, and I want to leave some room. So mass is just the total mass of this thing, and the volume of this thing is the volume of a cylinder, which is going to be pi r2 squared h, and then we just have to subtract off the size of the cylinder that we took out from the inside, which is going to be another pi r1 squared h, and we can factor out the pi and the h, and we get the total mass of the cylinder times pi h of r2 squared minus r1 squared. Now if I substitute that expression in for density over here, might as well make this 1/2. So we've got pi over 2 times h times the density, this big nasty thing here, so m all over pi h r2 squared minus r1 squared. And then I still have this, wait a minute, I screwed up somewhere. Yeah, these were fourths. There we go. All better now, no harm done, right? Okay, r2 to the fourth minus r1 to the fourth. And these guys go away, so that's good. And if we expand this expression out here, well, I've got a 1/2 m to begin with. This is r2 squared minus r1 squared times r2 squared plus r1 squared. And then we still have this guy in the denominator, and you probably see the end of the road here. These guys go away. We're left with this 1/2 mass of the total cylinder thingy, r2 squared plus r1 squared. And that's what we were trying to get to. Now that was just part A. Part B is to find the moment of inertia for a solid cylinder, which we've actually dealt with previously. But in that case, we could just rederive it, and we would change the limits of our integration, and we'd change the definition of our density, where we take that part off, right? But we might as well just plug in a 0 here for R1, and so for part B, it's just going to be 1/2 mr squared, where r is the radius of the cylinder if it's a solid cylinder, rather than one without a hole in the middle. Okay, so these can be a little bit tricky. They take some practice, but something that'll be good to learn. All right, a couple of other theorems that are going to be really useful. This one in particular, the parallel axis theorem. This is going to be one of your best friends. So if we know the moment of inertia about the center of mass of some object, then we can find the moment of inertia about any other axis of rotation that is parallel to this axis, just by adding this factor here, the total mass of the object, where h is the distance between the center of mass axis, between ICM and the new axis of rotation. Now that is probably not clear at all, but I will do an example and life will be better. So if we have a solid cylinder, which we just talked about, and we know the moment of inertia of a solid cylinder spinning about its center is 1/2 mr squared, and we're just going to call it r naught squared to be specific to this one. So that is the moment of inertia about the center of mass. Well, what if I'm not rotating it about the center of mass? What if I've got it like glued to some pole or something, and that whole thing is spinning around, so the cylinder is going around and around this pole here, spinning around its outer edge? That will probably have a different moment of inertia than spinning it around the middle. Likely it would be harder to rotate it around its edge than the middle. It would be harder to get going. So we can use the parallel axis theorem, which says that the moment of inertia about any other axis, now it's got to be parallel to this one. I can't take it like an axis here and rotate it about there. That won't work. Parallel axis theorem doesn't apply to that. So it's got to be parallel, hence the name. Anyway, we just take the moment of inertia about the center of mass plus the mass of the total object times h squared, where h is nicely defined for you here, the distance that we are pulling that axis of rotation. So in this case, we can go ahead and plug in. It works for more than just cylinders, by the way. This works for any object. We're just using the cylinder as an example here. So 1/2 mr naught squared. Then we're going to have m, and the distance h is the same as r naught, so we just get another r naught squared in here. So we have 1/2 plus 1, so that becomes 3/2 mr naught squared. As I mentioned, it should be a little bit larger, and it is 3 times larger. So there you go. This is a very useful tool that will come in handy and make really hard things simple, because if you had to integrate around that point, no, don't want to do that. So one more theorem that is nice, not quite as great as this first one, but this is called the perpendicular axis theorem. By the way, this is really only good for very thin objects. Thin objects only. Okay, so if you imagine like a coin, that would qualify as a thin object. And what it says is that the moment of inertia about the z-axis is equal to the sum of the moments of inertia about the x and y-axis. So that's why it's called perpendicular, because z is perpendicular to those two guys. This is typically, in the types of problems we'll see, usually going to be used where ix equals iz, or sorry, not iz, iy. So you're going to have a high degree of symmetry, which is the case for this coin example here, right? Spinning it around this axis would not be any different than spinning it around this axis. So if we make that assumption there, then we can say that iz equals 2 times ix, or iy, whichever one. And in this example here, this is just a disk again. The thickness doesn't matter for our moment of inertia about the center of the disk here. So even though it's thin, we still have 1/2 mr squared. And so if we know that one, we can find the moment of inertia about x or y by using this nice little formula here. So the moment of inertia about either of those is 1/4 mr squared. So that's how that one would be used. And that's all there is for this time. See you next time.